everything correctly? Full screen?
Yes, we can see the screen clearly. Also, with your permission, I would like to record this session. Although I have started, but I need still seek your permission.
Yeah. So it's no problem. Thank you.
Thank you. That's great.
Okay, great. So I will try to keep, as we were discussing with Dr. Gupta, that there is not a very defined time, but I will try to keep the whole presentation within 1 hour. And this is basically, let's say, focus on 6G from the point of view of micro and nanotechnologies for a quite unprecedented point of view compared to what is going on mainly in this field. And this all comes from basically my involvement. You can see here also the logo of the IEEE ComSoc, because this is a sort of summary of the distinguished lecture program that I developed for the 2 years, 2025 and current 2026. And basically, this is just a brief slide about my background. So this is just to say that actually I'm discussing 6G, but from a very low complexity point of view, because I have been developing basically MEMS, microsystems, mainly in the domain of radio frequency and energy harvesting in the past. So it is quite, let's say, a fresh vision about 6G from the very bottom of the chain. And this is basically a summary of the presentations that I worked on for the distinguished lecture program. There are basically 5 different presentations, and today I will try to squeeze all these topics in one unique webinar in such a way that you have, let's say, my aim is to provide you with a broad overview about this vision and considerations about the role of micro and nanotechnologies in 6G, in edge intelligence, development of IoT, and so on. Basically, the 5 lectures are, the first one is about framing 6G and future networks as a whole. So from the point of view of the KPIs and key enabling technologies that are currently under development. Then I will spend some time to introduce micro and nanotechnologies, mainly microtechnologies, for those who are not familiar with this very broad topic. Then the third one is about developing conceptual tools in order to link microtechnologies, which are typically used for very low complexity hardware components like sensors and actuators, with the very complex and high-level scenario of 6G applications. The fourth one, presentation is about reporting practical examples of already existing MEMS-based devices, which were discussed in the literature, and that can be suitable for employment and for empowering some branches of 6G. And the last lecture that I hope I will have time to cover too is closer to my direct field of expertise, because is actually a vertical focus on RF MEMS. So basically on MEMS devices for radio frequency applications, which are, of course, also can be a key enabling technologies for 6G. So let's start from the first very general one about 6G. So there is a discussion about 6G that is ongoing since years, and the scenario that is actually developing is very complex. If we want to simplify the most 6G, we can say that it will follow 2 different directions. On one hand, there will be continuity with the previous generations, so with 5G and what was before, with an increase of the key performance indicators, which is expected to be from 100 to 1,000 times. On the other hand, 6G is going to develop a lot of disruption for what concerns the massive exploitation of artificial intelligence in each level of the network, and we'll see it more in detail later on. There is also a discussion which is pretty much developed now, even if we are not yet in this phase of standardization, but there is quite a pretty clear view about what will be the typical KPIs, so the key performance indicators for 6G, and in this table you can see the transition from 5G to 6G. It is actually relevant to stress that this table was taken from a paper dated in 2020, one of the key papers which were developing visions about 6G in that time. And if we compare these numbers with what is discussed today, we are very close to what is going to be, let's say, brought to the next level. Okay, we all know which were the direction following the development of 5G, so I don't want to spend too much time on this. This actually was taken from the IMT 2020, release in 2015. And this is functional just because if we compare this with the IMT 2030, so actually with the indications for services and technologies that will be incorporated in 6G, we can still see the famous triangle of 5G, but with many other items in terms of use case and application scenarios, most of which are basically empowered and enabled by AI. Still referring to the IMT 2030, it is very nice to take a look at the so-called palette diagram, which is basically framing the most relevant KPIs, which and the development direction which are expected for 6G, and those are compared to what it was actually defined for 5G. And let's say, for the discussion that we are going to develop today, I would just pick one of these items, which is the forecasted density of devices, which is supposed to range from 1 to 100 million devices in 6G. This means that we'll have something like several millions devices, which are physical devices, which are connected to the networks, which must be able to sense some magnitudes, to perform computation of data, of information, to store data, to be powered, of course, and to be connected with the network. So this gives you an idea of how massive it can be in terms of hardware development, also meeting the requirements for distribution of edge intelligence and edge functionalities in 6G. Now, another, let's say, interesting statement that has to be developed is to compare what, since, also in 5G, there was a lot of discussion about key enabling technologies that in the end will not be developed under 5G. It is also wise to compare which were the main keys of the first discussion, of the early discussion of 6G, what is ongoing today. To this end, I take, let's say, some technologies, some key enabling technologies which were envisioned back in 2019 in this very interesting and very relevant paper. And you can see high-level application like extended reality, connected robotics, blockchain for security purposes, high-frequency operation, large intelligent surfaces, which today are more commonly referred to as RIS, edge AI, and energy harvesting. Now, this other table is taken from a more recent paper, which was released in late 2024, which gives basically a very broad discussion, a very broad overview of what is going on in these days. So which are the main initiatives worldwide, both concerning, let's say, governative projects and also private projects, to develop some use cases, to investigate and develop some use cases relevant for 6G. Here, I just took one of the tables which are available in this paper, and you can see worldwide that the keywords, and the main key enabling technologies which are being investigated are very well overlapped with let's say the very early visions of 6G. This means that actually the phase, the initial phase in which new scenarios and perspective papers, very relevant perspective papers, were published on 6G, was actually very close to what it seems to be going on today. Yeah, I also want to highlight that most part of the discussion that I'm going to develop, I had the chance to publish it in some papers and also in a book. In particular, these two papers on the proceeding of IEEE and IEEE access are open access, are both open access. So if you want to access them and take some, let's say, deeper look into them, it is possible to do it. And now I start discussing a bit more into details the key enabling technologies for 6G. So as it's already emerged, that 6G is a very complex scenario. So it is wise to introduce some sort of categories in order to see, to better understand what is going to happen. To this end, it is very useful to reason in terms of paradigm shifts, which will be introduced by 6G. And in this, let's say, in this early work, which was somehow further developed in this other work, which is one of the articles that I mentioned, there were four main paradigm shifts which were introduced, which are named scatter intelligence, seamless coverage, spectrum diversity, and enhanced security, as you can see in this graph here. The first one, scatter intelligence, is basically what I was mentioning in the very beginning. So is the exploitation of AI in a very massive way in 6G. This means that diversely from what is going on today with services, where actually AI is really very broadly used, 6G will leverage a lot on exploitation of artificial intelligence in the network operation. So in optimizing the network functionings and let's say also to enable a higher level of resilience in such a way to maintain the KPIs stable with respect to some variables which can happen, like increase of users for some specific reasons, availability of energy, of bandwidth, and so on. Another key of 6G, another paradigm shifts will be seamless coverage. So it will be basically the pursuance of ubiquity, which was already introduced in 5G, but it is clear that 5G will not manage to score it. This means actually having the same KPIs in terms of access to the networks, regardless of where a user or a machine is accessing the network. This means having the same performances, regardless if one is in the metropolitan area or in a rural or remote area. This will be possible through a highly diversified infrastructure that you can see here, which is not relying exclusively on terrestrial radio towers, but also on airborne device, on satellite. There is a lot of discussion and development in NTN, non-terrestrial networks nowadays, and notably also over sea, with a coverage basically also on the sea. Then another shift will be in spectrum diversity. So of course the volume of data will massively increase. There will be also very strict demands in terms of latency, reliability, and stability, end-to-end access, and so on. So of course there will be, and it's already developing nowadays, an exploitation of higher frequencies in higher frequencies bands, which are currently, let's say, unlicensed and also partially explored for the transmission of data in 6G, with frequencies ranges as high as the sub-terahertz and terahertz range, and also the investigation of optical communications, including visible light communication. Finally, all these, let's say, scattering of information and distribution of data information will bring to critical problems and concerns in terms of privacy, security, and trust. So, of course, another paradigm shift will be in ensuring the security of data, with technologies like blockchain, which is already investigated, and let's say differently from what has been going on up to date. The technologies to ensure will, let's say, the security and trust of data will be closer also to the hardware level. So it will be not only algorithms like blockchain solutions, but, for example, quantum technology. So physical devices which by themselves enable a higher level of security and also, let's say, the so-called physical layer security, so the incorporation of security in the physical devices. Okay, just to conclude this part, here you can see a crossing between the paradigm shifts in this sort of silos type representation and of key enabling technologies and technology trends. So basically, this is a list of the main key enabling technology and technology trends, and you can see quite a significant part of what was already discussed in the very early days of 6G, probably with some slightly different names, but this is basically the scenario, let's say, just framed in one picture. Now I switch to that second part, so to a summary of the second lecture. So now we are actually doing a sort of dive from very high level applications and paradigms to the lowest complexity of very tiny physical devices, and this gives me the opportunity to introduce, let's say, the concept of MEMS. MEMS is an acronym which stands for micro-electromechanical systems, also addressed as microsystems. And basically, these are devices which are fabricated, microfabricated with let's say, with most part of classical semiconductor technologies fabrication steps. And they differentiate from, for example, from transistors and diodes, from CMOS circuits and so on, because of some specific fabrication steps which are dedicated to MEMS. They are very tiny devices whose dimensions can range from micrometers up to a few millimeters. And their characteristics is the one of having always a movable part. So they always have a transduction between the mechanical domain and some other domains like electrical, electromagnetic, chemical, and so on. So if we recall how a classical CMOS transistor is fabricated, we can just understand how the technologies are let's say, how they differentiate. we can state that actually a transistor is built within silicon, because we all know that we have some areas with a specific doping which gives some wanted electrical semiconducting characteristics. So we have the core device which is within silicon. Then, of course, it is quite, let's say, relevant to see also in terms of dimension how different is the intrinsic device with respect to all the backend which is needed in order to route the electrical signals and contact the proper terminals of the devices in order to heal the more complex circuits. Basically, in the case of MEMS, we have a different situation because we can reconduct the fabrication of microsystems to two different technology platforms. The first one is the one called surface micromachining. In this case, we can state that the device, different from transistor, is made above silicon, because silicon or other materials, because of course the wafer can be also of quartz, glass, sapphire, and other materials, SOI and whatever. Basically, in this case, the substrate, which very commonly is silicon, is a sort of plane, a sort of desk above which the device is fabricated. Here you can see typical surface micromachining technologies, which is actually the one that we have at our institution for fabricating RF MEMS. So basically, the key is having a sequence of selective deposition and removal of very thin films, both conductive and insulating, so metals and dielectrics. And in the end, we healed a mechanical structure, which is released. In our case, this is done with electroplated gold. So in the end, we have basically a suspended membrane which can physically move, can physically be deformed, which heals our device. The other very common way of fabricating MEMS is through the so-called bulk micromachining. In this case, the actual MEMS device is made of silicon because we are using the substrate, the silicon substrate, as a structural material for realizing our MEMS device. So in this case, with a very controlled and high aspect ratio hatching technique, it is possible to release suspended structure made of silicon. Here you can see a photograph, basically a SEM image of MEMS-based micromirrors, so very flat, square mirrors which are suspended with flexible structures. And in this way, it's possible to heal our MEMS device. Here you can see a typical design and fabrication flow of bulk micromachining MEMS devices, which is based on SOI, so a silicon on insulator wafer, and with some, let's say, deposition of metals for, of course, for routing electrical signals. And at the end, with the etching, selective etching of silicon, it is possible to release the MEMS structure. Concerning operation of MEMS, they can be actuated in different ways. This also introduces a lot of degrees of freedom in order to optimize the design and the working principle of the devices, because we can have the electrostatic actuation, which is actually the mean that we use in our facility to actuate our RF MEMS. We can have electromagnetic actuation, so sensitivity to a magnetic field. Piezoelectric actuation is also very common, which exploits thin films with piezoelectric actuation, both for actuation and sensing. And finally, we also have the electrothermal actuation. In this case, we use a thermal expansion of some films in order to have a deformation of device, and in this case, actuation. In this unique example, the closure of a micro switch. Concerning electrostatic MEMS, they have an hysteretic behavior. So when we actuate them, we have a pull-in and pull-out voltage, which are not the same. So we have this hysteretic behavior, and this is just to introduce the next slide, which is actually a video. This is a video which was reconstructed years ago with an optical profiling system, a dynamic system. In this video, you will see the response of an RF MEMS switch to a triangular voltage, which is crossing the pull-in and pull-out levels. So I just started. In this case, you see that the switch is actuated. When the voltage is decreasing, it releases. So this is its rest position. Now the voltage is still increasing, bringing the switch to the actuation. And now we'll see again the release of the switch. So this is actually the reconstruction of the dynamic behavior of a switch. We are talking about a vertical movement of about 3 microns, while the dimension of the switch, just to give you an idea, is about 120 micrometers by, 150 probably by 150 micrometers. Now, a few words about how MEMS developed in the market. I took these slides from an intelligence report from YOLA Development, which is quite old, dated back in 2017, but it gives some very relevant classification of how MEMS developed and how at the time they were supposed to further develop in the future. Basically, YOLA was correctly identifying different waves in the development of MEMS. Basically, the first wave was mainly in the 90s, late 80s and 90s, where actually MEMS were successful in the market, mainly in the automotive sector for the inertials which are deploying the airbags, but also in projectors with the MEMS-based micromirrors, and in inkjet printers with the nozzles for dispensing the ink on the paper. This was making the first success of MEMS from the market point of view, despite MEMS started to be investigated in research already in the 70s. Actually, even earlier, if we refer to mechanical properties of material. Then there was a second wave of MEMS, which was, let's say, after 2000. In let's say in the first years of the new millennium, with consoles. So once again with inertials as the key component. First with consoles, gaming consoles, and then with the development of let's say smartphone, the early smartphones which were incorporating inertial sensing capabilities and stuff like that. And then at that time, we must remember that this scheme is dated back in 2017. It was actually forecasted that robotics, virtual reality applications in the future would have a demand for a larger number and volumes of variety also of MEMS-based devices and sensors, and this is actually what somehow is happening. Okay, now I switch to the third lecture. This will be quite brief because it's more conceptual, but here the idea is after having seen these two very distant scenarios of 6G and key enabling technologies and functionality of 6G and microsystem-based sensor and actuators, it is necessary to build some links between these two very far away realities and scenarios. This is once again what, let's say, as I mentioned before, is something that you can find into more details in these publications. But to do this, there are some conceptual tools which were introduced in these publications. And I go very quickly through them just to provide, let's say, a few hints about what is their aim. The first one is called the core versus edge model, which is basically an empirical description of how the telecommunication standards evolved from 1G to the current 5G and how they will evolve in 6G and future networks. From the point of view of, uniquely from the point of view of distribution versus centralizations of data and of exchange of information. This is quite important because, let's say, if we actually witnessed, let's say, after 3G, from the more or less from the third generation, we witness a significant tilting towards centralization of data. Already with 5G and more importantly with 6G, there will be a sort of reversal of this trend with much more distribution of data. Still with a lot of central orchestration of the network, but with more and more data information which are distributed locally and locally managed, computed and stored. Then there is another conceptual tool which is called the identifying, define, deriving methodology, which is basically a sort of framework in order to start from very high level requirements of 6G, which are defined as critical mega requirements, then stepping to the technology trends which are triggered by these requirements, and finally stepping towards definition of functional features, mainly for low complexity components. This is basically a way to start from high level requirements and specs and find a way to, let's say, translate them in what is expected to be in terms of functionalities and specification and performance, of course, of low complexity hardware and physical components. Then another couple of trends which are identified are more related to the let's say, to hardware software systems. So to how hardware and software functionalities combine together, and still keeping in mind the massive increase of distribution of intelligence and of physical devices, still recalling the 100 million devices per square kilometers as forecasted by the IMT 2030. These trends actually go in the direction of having more flexibility in the combination of hardware software. So somehow they are overcoming the hardware software co-design approach, which is very effective. But in order to make possible more flexibility of functionalities between hardware and software, the idea here is to have a more dynamic combination of software and hardware segments in order to trigger new functionalities and step towards what also AI is expected to bring at the low level of the network. This will be possible through more symmetry between hardware and software components, which means, and this is actually the key of micro and nanotechnologies, so it will be possible by incorporating more functionalities at the hardware level. So this will mean actually having more resident functionalities in the physical device rather than making possible those same functionalities with the subsystem. So with the more complex entity, which has some, let's say, for example, microcontrolling units, some backup devices, some additional sensors and actuators to deploy some strategies in case of need. So this is something that it will be probably clear in the next part of the presentation with some practical examples of MEMS devices. And okay, the final conceptual tool is called the Wi-Fi ecosystem. So this is basically a sort of a parallel between the functionalities that will be needed in 6G for low complexity hardware components and the 4 classical elements in nature, because some of these, let's say, some of the characteristics, for example, of water and of fire are similar to what it is expected in terms of flexibility, adaptability, resilience, and the differentiation of functionalities for low complexity hardware components. So this brings me to the lecture 4. Now I would like to report a few practical examples of MEMS devices for this vision of 6G and of edge intelligence. And what I must say is that all these examples are not related to 6G. So these are all examples which were developed even quite a long time ago. Some works are older, more than 10 years. But these technologies, these materials have characteristics which can go in the direction of what it was discussed in the very beginning for 6G, especially with reference to the edge of the network. So the first example is at material level and is related to self-repairing and self-healing properties of materials. Okay, here you can see there are all the references reported here. The first example is about using carbon nanotubes in order to trigger self-healing of electromagnetic properties of some materials. And in this paper, actually, there is yes, a material which is supposed for electromagnetic interference, which is intentionally damaged, reducing the isolation, the electromagnetic isolation ensured by the fresh material. And just with heating, it is possible to trigger a self-recovery of the material, which brings back the electromagnetic properties very close to the initial one. Another example is the one of self-healing liquids in dielectric layers. So basically, here the idea is to have a thin film of dielectric layer, which is subjected to quite large electric field for a long time. Typically, if there are some voids, some imperfection in the material, the continuous stress, electric stress, brings to the formation of treeing, so of cracks, which are actually developing through the material, and which in the end bring to the total failure of the device, so to the breakdown of the dielectric. In this work, which was quite, let's say, quite impressive, there were some reservoirs of healing liquid which were embedded in the material. in such a way that when the trees are developing, so when the cracks are advancing through the materials, at a certain point, they reach one of these reservoirs, they break the membrane, which is keeping the inning liquid inside, and the liquid is filling the treeing, blocking the advancement of this problem. Here it is another example which relies on silicon carbide material to basically trigger self-healing mechanical properties. So in this case, what is recovered once again after intentionally damaging the device, and is a recovery of the mechanical properties of the material, still thanks to these, let's say, specific micro materials. Then another interesting feature of let's say, that can be enabled by micro technologies is the one of having multifunctional devices. So in this other example, which you can see is 10 years old, it was presented at technology, a microfabrication technology, which is quite complex, but definitely feasible, which made possible to incorporate 5 different sensors, an electric field, accelerometer, humidity, temperature, and pressure sensor, within a 10 by 10 square millimeter silicon chip, using a combination of surface and bulk micromachining. And here you can see the, let's say, all the relevant fabrication steps, both for what concerns the surface micromachining for the sensors, and then the bulk micromachining for inertial sensors, and also for the packaging. And this made possible how it is actually feasible to have different devices, also characterized by different operation way, because here we have capacitive, piezoelectric, and resistive transducers within a unique silicon chip. So imagine to have something like this in edge devices, where probably there are some redundant and not necessarily needed types of sensors, but in case that node has to implement a different function, it is possible to wake up other sensors and implement that function. Another relevant example is the one of memories based on micro and nanotechnologies. Here you can see examples which are exploiting micro and nano switches to yield both monostable and bistable memory units. This it was investigated for a long time. This paper is dated back in 2008, and let's say MEMS-based memories actually were not as successful as expected in the beginning in the market, but differently from let's say semiconductor-based memories, they make possible to have an integration with other similar devices. So if we think that MEMS is also investigated for logic devices, so for logic gates, it is possible to imagine to have computation and storage of data within the same device, which would be definitely interesting for this large-scale application, like it will be in edge devices. Then another crucial part is the one of energy, and MEMS devices were investigated and were successfully investigated also for the realization of energy harvesters, so of small converters which are able to address some environmentally available source of energies like vibrations, thermal gradients and so on, and convert part of this energy into electricity. So there is a lot of discussion, and actually there were also some commercial devices based on MEMS technology, and this is also can be regarded as a crucial technology for making edge devices in 6G energy self-sufficient, because of course it is unthinkable to have to wire such devices or to have batteries to be replaced from time to time on such large numbers. Now, the last part of this section is about actually a few examples, because up to now I was discussing, let's say, technologies and sensors and devices with some features which goes in the direction of the vision of 6G. Now I focus on some combination of different functionalities within unique devices, which gives you already a sort of preliminary idea of how subsystems could be implemented in a unique piece of hardware, rather than being distributed over different devices which are integrated in the sensors. Sorry, in a system, in a subsystem. This example, which is quite relevant, is of a self-powered accelerometer. So here you can see a typical implementation of an inertial sensors with suspended proof mass and piezoelectric elements for sensing the acceleration. But the addition in these devices is also the use of electromagnetic transduction with this coil deployed underneath, because actually the piezoelectric transduction is used to sense acceleration, while the electromagnetic coupling is used to extract energy from the functioning of the device. So basically, this is an example of a sensor which is powering its own functioning when it is functioning. The work also reports about the controlling electronic of this device, which is compensating the fact that energy is extracted from the electromagnetic transducer in order to power the device and correct the reading of the acceleration. And but this is a quite relevant example of a subsystem which is realized in a unique device, rather than having also a powering unit, battery, let's say, a more complex system. Another relevant example is the one of an inertial MEMS device, which is implemented with a series of cascaded switches. So this example actually, different from classical accelerometers, is able to perform already within the device itself sort of digitalization of the acceleration reading. So this is not the classical analog accelerometer, which then needs some other blocks in order to convert from analog to digital the reading signal of the sensor. But it is already providing a quantized level of output voltage, which correspond to the acceleration which was sensed by the device. And the final example is the one which goes in the direction of computing in memory. So, and also goes in the direction of non-conventional computing, because this is actually based on nanostructured gold films, in which micro and nano joints between grains of the gold are used in order to implement a complete set of Boolean function. So in this case, of course, the device is quite, let's say, unconventional, because it must be characterized, let's say, any replica of the device is different from others, because you have a very complex distribution of the gold clusters on the film. But it is possible to map a complete set of Boolean function, and this goes in the direction of having very, very tiny components, which are as simple as thin films of certain material, in this case gold, which can implement some logical functions. Okay, now I step to the last in these last minutes of my webinar, to the final part of the presentation, which is about RF MEMS. So here, the idea is to provide some vertical insight about these technologies, which is the one that we developed in our facility on our surface micromachining process. So basically, RF MEMS are MEMS devices that realize radio frequency passive components, which can be as simple as micro switches and variable capacitors, but more interestingly, can be combined in more complex topologies by using several basic components, and yield highly reconfigurable devices like switching units and matrices, step RF power attenuators, delay lines, and so on. Now, if we focus again on 6G, it is clear that that there is already today an ongoing development which goes towards massive MIMO types of antennas, and also towards needs for beamforming, advanced beamforming for small and picocells. So basically, this is yielding a lot of efforts in research, especially for what concerns beamforming, which can be pursued in analog, digital, or in hybrid ways, leading to a certain complexity of the devices. In essence, basically, we have the antenna, which is composed by several elements, and in order to have beamforming functionalities, in principle, every element of the antenna, but let's say easily in a more in a less complex way, parts of the elements of antenna must be fed with signals which are delayed and which have a certain amplitude compared to the other signals which are feeding other elements of the antennas. This brings to a quite complex chain of components which need to be connected to these antennas, which feature power attenuators, phase shifters, and switching units in order to have the operation of antenna both as in reception and transmission. And if we think of applications which are venturing higher frequencies like sub-terahertz, so hundreds of gigahertz, of course, losses, power consumption, and integration problems can be very relevant. And the classical approach based on discrete components which are integrated together is, let's say, less and less feasible. One solution could be the one of exploiting a technology like RF MEMS in order to have integrated devices, so within a unique silicon chip, to have all the functionalities related to power attenuator, phase shifters, so delay lines, and switching units. So this is actually possible with such a technology, and this would bring a significant simplification of the hardware complexity of the devices to be connected to the antenna. Also, and this is the last example that I want to report today, it is also possible to have an integration of RF MEMS with the antenna itself, because as much as the operation frequency is increasing, the dimension of the antenna is basically squeezing down. It's less and less bulky. So at a certain point, it's possible to have, and this is an example of a work that we published quite recently. In this case, we actually demonstrated an antenna with RF MEMS switches integrated in order to have an activation, controlled activation of rows and columns of this antenna in such a way, basically, to change the dimension and therefore the resonant frequency of the antenna. Here you can see some fabricated devices in our facility, and you can see from the preliminary testing on the S11, so on the reflection, you can see that depending on the number of activated columns, it is possible to have a resonant frequency, a negative peak, which corresponds to the transmission of the antenna, which is ranging from around 8 gigahertz up to more than 30 gigahertz. So this is also an example of how this technology could be further developed and bring some significant value in low power and low complexity, low cost nodes, physical nodes needed for the edge of 6G and of future networks. Okay, with this I conclude the presentation. I thank you for your attention. I managed to stay within 1 hour, and yeah, thanks again. And if there is any question, I would be happy to address them.
Thank you, Dr. Jacopo. I would like to say thanks to you for this wonderful presentation, and it was really a very concise one within precise timing. And the way we were stepping forward towards the final conclusion of the series, it was very interesting and engaging. So first, I would like to invite our participants to have some discussion with Dr. Jacopo on to the topic and about the presentation. I hope some of us is having the question. Yes, Dr.
Yeah, we have one.
First of all, thank you very much for the exciting presentation.
Thank you.
I have no specific questions because it's so exciting, mainly the resonance frequency part of antennas. We are doing, in my lab, we are doing mainly the nanosystems, nanostructures based on graphene silicon by laser plasma, and trying to prepare the also materials for MEMS. So it was very helpful to listen what are you doing and how are so that you are, and may I say that you are in front of this kind of developments, and thank you very much once again. Thank you very much indeed for me again. This is many questions, of course, because it's huge information. Mainly, I had the questions, but it's necessary. Maybe I will send you the special mail about that, about the preparation, how it works with the liquid phase of carbon nanotubes, how is this mechanism is working to prepare for preparation of sensors and transducers. So thank you very much again. I'm professor from Georgian Tech. So thank you, and I am giving the floor to others.
Thank you. Thank you, Professor. No, I just want to, let's say, thank you for this comment that you had, because This is actually the idea also behind this distinguished lecture program and preparation of material on my hand, because what I feel is that there is a need to build links between people that typically are working on very fancy technology stuff, but probably without a unique umbrella in terms of application and direction. So this is great, actually, having this positive feedback from you, because a way could be, let's say, bringing micro and nanotechnologies. So typically things which are discussed in a very well-defined community, and have interaction with people who are working at a definitely higher level of complexity, and somehow being unaware of what is possible to do in the, let's say, in the small world. Let's call it this way. So thank you.
Yes, thank you again. Thank you again. And we're mainly using the laser-induced processes in any technology, even in nuclear fusion, you know, yeah? So, and we're preparing this different lasers, different technologies, and for so-called spintronics application also. And maybe it will be some bridge. It should be, I mean, they build some bridge in between the sensors and spintronic device. Yeah. Thank you very much indeed once again. And Dr. Gupta, thank you very much for your reminders.
Thank you, Professor Petta.
Give me the possibility to come to your webinar. Thank you indeed.
Definitely. That would be very great, and we will be very much obliged to have you on board.
Thank you.
And I would also, I can see there are many thanks messages into the chat to Dr. Jacopo, and everyone is praising the way you handle the webinar. Moreover, very basic question, because there are many mix of scholars also into this webinar. So how the softwares are able to handle these kind of complexity into the initial stage of designing? Because we directly don't jump into the hardware. We try to simulate the design and then come to the final fabrication and chip designing part. So how does those softwares are able to handle that much of complexity and to simulate the challenges which we actually face into the real application areas?
Well, it's actually a very good question, because of course it goes in parallel with the technology development, because you know, there are very well-defined techniques for simulating and predicting the behavior of devices from the physical level to the operation level. But as much as you step higher in complexity, it becomes quite difficult to have a unique framework in order to predict the behavior of such complex systems. For example, we develop, we work on technology, so we typically use simulation in the physical domain, the mixed domain, so mechanical, electrical. You know, already simulating an RF MEMS is quite complicated, because you have the mechanical, the electrical, and the electromagnetic behavior, which are all mixed together. And typically you don't have a unique environment, a unique software tools that you use in order to have an optimization. So you should run some sort of cross optimization across different softwares. Then, of course, there are also, let's say, AI and machine learning technique, of course, can help a lot in this direction. For example, I see that there is also Professor Marinkovic from Niš University who is was following the webinar, and we are, for example, working together with her in applying artificial neural network techniques to the prediction of RF MEMS behavior of some devices. But this is still based on the device level. Of course, ranging up in complexity brings also the need for probably unconventional approaches to the simulation of description of such a devices. So it's it's also a very exciting part of this development, which needs somehow to be addressed with some new approaches.
Right. So, like you have mentioned, Professor Zaletica is into the webinar, and so I would like to personally invite Professor to comment on to this particular complexity scenario of the simulation environment. So, may I, Professor Zaletica?
Hello. Good morning, everybody, and thanks, Jacopo, for giving such an interesting lecture. I always hear from you something new, now something from 6G, and thank you for the organizers for letting me join this interesting webinar. Actually, I am in my research. I'm doing research on application of artificial intelligence and machine learning to make new models of different semiconductor devices, transistors, and now for MEMS devices. What is the advantage of such models is that they are, once developed, they are much faster than traditional models, but from the other hand, you need still to perform simulations in traditional tools that will gives us data to develop the AI-based models. So a lot of advantages, but also a lot of challenges to develop models. So we have started the project last year, and it is a three-year project. So we hope that we will have some interesting results to show.
Thank you. That's great. Moreover, I would like to just add one question from my side once again. I have seen few publications over this area. In those works, they have simulated, they have collected the data, and they use the prediction using machine learning model to predict more parameters tuning or something similar to fabricate the new designs into the simulation environment. So that kind of usage of AI with the limited data sets is personally I feel is very challenging, and that brings the solution or prediction output into the low trap. We can say into the local trapping, because with the lesser data and predicting the new modeling is quite challenging, and sometimes might lead to inaccurate result also. So collecting, like Professor Zaletica has suggested, collecting the data from training the different machine learning models for this kind of fabrication activities or simulating the models before fabrication is backed by the lack of actual real data. I think that's the way, the field where if we want to integrate the AI into the simulation part, then a lot of data collection activity need to be done from different labs to a unified place, so that data can be collectively used to train the models and to predict the complexity, and because with the evolution of graphical deep learning, the graphical networks, because everywhere we are seeing that. So with the evolution of graphical network, the connecting points should be very high, so that we can come up with a new set of features and attributes and a new vision for the designing. This I feel with the integration of AI can be very much helpful into the MEMS technology.
Yeah, actually, if you develop model which includes and considers geometrical or other material parameter of the devices, then you will have models which can be used for further optimization, and they are much faster than traditional ones. But as you said, you should be very careful with simulating the data that are used for the networks, and which is more important to properly test your model with the unseen data to be sure that generalization is good, because it's not a problem to learn the presented data, especially with some bigger models, but it's a problem to have reliable model. And that is the point where the attention should put. And we are still working with the simple multi-layered networks, but as you mentioned, graph networks and the other networks are also promising solutions. So thank you also for suggestion for us.
Thank you.
Yeah,
Thank you.
and if I can add, let's say, add on it, we also must remember that we are dealing with micro and nano fabrication at the end of the day. So having a lot of data in order to train this model from physical devices is very costly and let's say and time consuming. So it's not viable. So once again, having already some simulations, traditional, let's call it simulation approaches, which are quite tested and validated and accurate, is crucial also to produce a large amount of data sets to be then used for training this AI-based model and machine learning models. So once again, let's say the traditional ways like finite element method, so physical-based approaches are also, let's say, crucial. They cannot just be replaced by machine learning approaches, but are very useful in order to also to diversify the amount of data which are provided then for training and to have more robust models in the end.
That's true. That's true. Everywhere we cannot use machine learning model due to shortage and limitations of the cost and the process of time, which includes into data collection. That's very much true. That's why I think this field is still working on to the testing with the physical experimental lab.
Yeah.
Thank you. Thank you, Dr. Iannacci. So, is there any more question to discuss with Dr. Iannacci, because we are still crossing the time limit, and I requested Dr. Iannacci for sparing 1 hour for us, but it is crossing the time. So, if there is some more question, please let's have a quick overview over those questions. I think there is no more point to discuss from our participant. And again, I would like to request Dr. Iannacci from the side of our participants, if there would be any question to discuss into the future also, I would try to share onto the email so that you can answer as per your convenient time to their queries and research-related inquiries. All right.
Sure.
So again, I would like to thank you everyone, and special to our Dr. Iannacci, Professor Zeletica, and Professor Preta, to contribute and share the insights of their research into this webinar. And very much obliged, truly we are, with your presence and great research journey to know about this field. Thank you. Thank you very much to everyone, and have a nice day. Thank you.
Thank you. Thank you, Dr. Grupla. Thank you to all the participants for this great opportunity of sharing some ideas with you. Thank you.
Thank you. Thank you, sir. Thank you. Bye-bye.
Bye-bye. Bye.
Goodbye.